Welcome to the second edition of Flat Earth Math. The subject today is not just what satellites are, but where are they? To start off, I'd like to go back to the things I learned in the Army about satellites. In order for a communication satellite to provide proper service, you need to meet the following stability requirements. The satellite must have a near circular orbit, which means that the apogee and the perigee have very little difference between them. This prevents orbital decay. The satellite must be geostationary. This means that the satellite's orbital speed matches the rotation of the Earth. So from the Earth's standpoint, it appears to not move in the sky. The optimum altitude to achieve a near circular geostationary orbit is 22,236 miles. And finally, to provide the widest range of coverage, the orbit should be situated around the equator. After learning that the Earth was flat, I started going back and looking over some of the old satellite radio communications that I put together when I was in the military. It's funny because, we just used the numbers. We didn't question where they came from. So I decided to go back and look at least one of them that I put up in Fort Richardson near Anchorage, and look at that one and determine if it met what I needed to get the proper elevation. Anyway, so I'm going to be using a lot of trigonometry, but I want to just, it's probably going to make your head spin, but I'm going to do it just because I want to make sure that people know where I got the numbers. And so anyway, if I look at the Anchorage radio communications that I put together, since Anchorage is situated at almost 60 degrees north latitude, the elevation of the antenna will be nearly zero. The distance from the center of the Earth to the satellite that it's pointing at is going to be 7,918 miles. So to get the height of the satellite above the Earth, you subtract the radius of the Earth. So 7,918 miles minus 3,959 miles equals 3,959 miles. While this does put the location of the satellite in the upper exosphere, it is certainly not 22,236 miles high. So what's going on here? I decided next I would look at my own TV satellite dish outside. So now I'm going to compute the elevation that my TV satellite dish needs to be to reach to a satellite at 22,236 mile orbit. And this is where the math gets really icky. So anyway, suffice it to say, we need to compute the height due to curvature, which we can achieve by computing 2 times the cosine of 47 minus 1, that total times the radius of the Earth, 3,959 miles, and we get 1,832 miles. Next, we have to account for an x1 factor. So we get that by multiplying 3,959 times the cosine of 47 degrees minus this h1 that we just achieved, and that's 868 miles. Then we add that to the height of the orbit, which is 22,236 miles plus 868, and that gives us 2,304 miles. Then we take the arctangent of 2,304 miles divided by 3,959 times the sine of 47 degrees. This gives it a phi angle of 83 degrees. We subtract the 33 degrees from that phi angle, and that gives us the elevation of the satellite at 50 degrees. I told you the math was going to be icky. So anyway, now that we know we need an angle of 50 degrees to achieve the elevation to reach a satellite orbiting at 22,236 miles above the Earth, let's look at my satellite dish outside. Here's a picture of the satellite dish on my house. I took a protractor template and laid it over the satellite dish, and it looks to be about 20 degrees. Oops! Looks like it's not going to be high enough to reach to 22,236 miles. So where is it actually pointing to? So Since we have a known angle of 20 degrees, I took the calculations that I did before for a ball Earth and redid the calculations the other direction. And when we get through, we come up with a height of 2,294 miles above the Earth. While my satellite TV dish is aiming somewhere in the exosphere, it is clearly not aiming at anything at 22,236 miles above the Earth. I don't know about you, but all this ball Earth trigonometry is giving me a bit of a headache. So, since we know the Earth is flat, what are these satellite dishes pointing to on a flat Earth? Let's look at my satellite dish TV again from a different standpoint. Using a calculation from the North Pole to the equator, 6,218 miles, we can compute the height of whatever the satellite is or dish is pointing to at tangent of 20 degrees times the whole of 6,218 sine 47 degrees, and this equals 1,655 miles. So let's have another look at that satellite dish at Anchorage. If the satellite on a flat Earth at Anchorage is pointing to something 1,665 miles high at the equator, then we can compute the angle phi for the satellite dish as 0.31 degrees, which is pretty close to zero. So, what could those dishes be aiming at 1,665 miles above the Earth? Well, my YouTube friend Geoshifter has some ideas.
Let's look at how satellites are made.
So what we've got here is the overall service module, or the startings of the service module of the telecommunications satellites. What you can see are 2 tanks of an eventual 4-tank propellant system. On the outside, in several locations, we've got 7 smaller thrusters, and we have a main engine, a liquid apogee engine, which is fitted inside the cone.
The service module carries 4 fuel tanks, all placed around the central core. Each fuel tank can withstand an internal pressure equal to being over 200 meters underwater.
That's it, we need big tanks that can take the pressure and fill those with helium. Not propellant, helium. Imagine they can lift the cat and take the pressure. Would the altitude keep increasing? Helium rises up because it's lighter than air, but if you look at the properties of the thermosphere, you will see that it's made out of mostly helium. So in theory, if you get there, at some point it should start to float. Yay! Our cat is floating! Now we need to get it in orbit. Well, I think that's a pretty simple one. If you look at the wind streams at higher altitudes, or even at most altitudes, you will see that it makes a big circle above the equator. There is this weather tool that allows you to see the wind streams on the flat Earth map, and you can clearly see it makes a big circle. There are also people that circumnavigated the Earth with a balloon and use those wind streams. It's also important we prevent the satellite from spinning. When I spin my cat around very fast, she gets dizzy and throws up. We don't want that. So I was thinking maybe we can use the solar panels like ailerons on an airplane and take more advantage of the wind. Or, just to be sure, we can add a tank of rocket fuel and some nozzles on every side. Well, that's how I would make a spaceship. That's ridiculous! Yes it is, but it's probably a lot cheaper than NASA. And I bet it's also a lot more fun. For cats.
So, are satellites actually balloons with a lightweight metallic skin instead of latex so they don't explode? Or could it be something else? Like perhaps ionospheric skipping. It's an antenna technique where you skip along the ionosphere. Let's say, for instance, that my TV satellite dish is pointing to a network hub in, say, Los Angeles, California. That's 961 miles away. That would put the skipping midpoint for a ionospheric skipping radio shot at 480 miles. Ionospheric skipping occurs in the F layer of the ionosphere, which is 93 miles to 310 miles up. When we crunch the numbers for the skipping midpoint, we get 175 miles altitude, which is pretty much right on the money for F-layer ionospheric skipping. So now we know what kind of altitudes we're dealing with these satellite dishes. And I've shown you a couple of ideas of what we could be dealing with these satellite dishes. And maybe you can come up with some more ideas of your own, because we're all scientists now. Bye.